Simon. I feel like
Okay, we're recording.
you want to introduce us today?
Sure. Welcome to day 4 of the crash course in propulsion. Today's the final day. So we got a couple things on the agenda. It's a bit of a short day, but moving down in the engine, we're going to go over the nozzle, then how we use CFD to analyze a nozzle and potentially other things, and then review O-rings, and then review testing requirements for testing and all of its purposes. And we're going to start with nozzles. So the nozzle is a hardware component that converts thermal energy to kinetic energy. And what that means is the thermal energy is the combustion that happens in the combustion chamber, and kinetic energy is those combustion particles moving at a high velocity. So it does this by changing the cross-section area of the flow that moves through it. From a converging, which means coming towards a small throat area, to a diverging, which is where it opens up. On the right here, you can see a graph that shows the velocity in blue, the pressure in green, and the temperature in red or orange as it moves along with through the nozzle. It's divided into two sections, where M stands for the Mach number. So it shows once it's greater than 1, it's supersonic. So you can see how it enters at a low speed, and then as the nozzle converges and the pressures and temperatures start to decrease, the velocity starts to increase. And then the velocity continues to increase as it exits the nozzle. And once these combustion particles exit, or just gas basically, exit the nozzle at a high speed, that's what the thrust actually is. So this is like the important part of the engine, where everything you've been doing comes out here and gives you the result of creating thrust and propelling your rocket. So there are two main types of nozzles. There are other more advanced and interesting types that have special situations where they'd be used. Mainly an aerospike is a common kind of like advanced rocket nozzle that's not used very much. But the two here are conical, which means it just follows a cone shape, and a Raoul bell nozzle, which is super common. You see it in most rockets most big rockets that you've seen, like SpaceX or the space shuttle with the RS-25 or such. It's kind of your traditional bell shape. But we use the conical nozzle because it's just super easy to machine. You don't need to worry about advanced like CNC machine techniques and stuff like that. So it saves us money and also makes our design a bit easier. And it's also still fairly efficient. So we identified two materials that we wanted to use for our nozzle. And they're identified for their ability to withstand the high temperatures of the combustion materials. And these two things are graphite and micarta canvas vanilla composite. So the one thing to note about the micarta is that it has a high erosion rate, which means that it's an ablative material. That means it deals with the heat by allowing the outer material to flake off over time. And it has a higher erosion rate than graphite, which means that more of the material erodes over time. So that means you can use the graphite longer and more often. However, the graphite is heavier, like significantly heavier. And it's also expensive to machine, because when you machine it, when you subtractively machine it, you get conductive dust particles that make a huge mess, and machine shops charge extra to clean up. So those are two things that go against the graphite. So one of the things so the erosion rate is really the strongest piece of the pro-con list here. We really want to keep low erosion rates. So at one point there was a design consideration where we'd have just a throat insert, where the whole nozzle would be made of this micarta composite material, but the throat would have a small section where we put in graphite But ultimately, it just became a really difficult design to execute on, and we decided to just stick with a graphite, a single piece of graphite that would be subtractively machined into the shape that you can see on the right, mostly just because if it's lower erosion rates. Okay, so the nozzle expansion, this is an important concept to understand, and really the graphic at the right is really just explains everything. It's the most important. But your nozzle geometry determines how efficiently the combustion gases are converted into velocity and therefore thrust. So what you're hoping is that as the exhaust gases leave the nozzle, you want the gases to be at the same pressure of the pressure outside your engine. So at the ground, you just say like that's just like sea level. And for our engine, we test obviously in the ground, and we fly to 10,000 feet, which in the grand scheme of things is basically just still sea level. So we hope we hope to use a expansion ratio, which I'll explain in a second, that has a geometry where the exhaust is at the same pressure as the atmosphere around it. So what happens, that would be this ambient nozzle, which is optimal and ideal. When you get pressures that are below atmospheric pressure, you get what's called overexpansion, where your exhaust kind of goes into itself. And if your pressure is too high, you get underexpanded, where the exhaust kind of expands outward, I guess. So I mentioned expansion ratio, and that's the ratio between the area at the exit of the nozzle and the area at the throat. So the throat, again, I meant to say this before, the throat is the area with the smallest area, which would be right here, and then your exit would be where this line is denoted, which is just the end of your nozzle. So we can get our, one extra thing is that if you have a severe a nozzle that's severely over or under expanded, will cause something that's called a flow separation, and this could actually damage your nozzle. So it's not purely just an efficiency thing. It also could cause damage. So it's important to keep that under control, and that's why we shoot to keep an ambient nozzle and the correct expansion ratio. So your expansion ratio can be derived from CEA, which is the software we've talked about several times before. And then you can also calculate it using some concepts that are taught in compressible flow classes. Continue. So here are some nozzle calcs, and this will kind of just show you the workflow. If you were to design a nozzle by yourself by hand, you could do it this way, and it shows how you would track through the whole process. We often just use CEA as a shortcut, just because it's just easier and quicker to get us like the expansion ratio, for example. But here, like you start with like a PE stands for exit pressure. So in this case, it'll just be the ambient pressure at sea level. And then here are an equation for your exhaust velocity. And then this is your exhaust velocity, but expressed in terms of its Mach number. So its Mach number is essentially a ratio of the velocity compared to the speed of sound. And then some of these other variables are, so P naught, T naught would just be your initial conditions, which in this case for a nozzle, the initial would just be the combustion chamber. R is your gas constant, and gamma is your heat capacity ratio. So you'll see these a lot more in your ME200 thermodynamics class, and you'll see it again when you take a compressible flow class, which will be going over like these exact equations. And then from these, you can deduce your expansion ratio using this extra equation, which again uses these terms and also your heat capacity ratio again. And then you have to use your desired thrust level, and you can determine your mass flow rate. So for your desired thrust level, we know for our engine, we want to use 4 kilonewtons. So if we continue to the next slide, we can then use many of the same variables plus your mass flow rate to determine the area of the throat. And then from the area of the throat and the previously determined expansion ratio, you can determine the area at the exit. You can verify that you have the correct contraction ratio. If your combustion chamber cross-section area is 3 times larger than the throat. So most of nozzle calculations are always talking about the diverging section, which is the throat to the exit, but there's also the converging section at the beginning where it goes from the combustion chamber towards the throat, which is also important to look at as well. And then you also want to look at, so when we say the nozzle profile, that just means like the type of nozzle. So for our case, we chose the conical, so we don't need to worry about the bell shape. We use just a conical at a certain angle where 15 degrees is what's super common for engines of our size. And that's the size we're using. So that's kind of just a quick overview of how you would get to design something that looks like this blue piece here. So some of the final properties would be an expansion ratio of 5.157, which means the area here would be about 5 times the area right there. The divergent angle, which is the angle this makes with the vertical, is 15 degrees. Then you have various other radiuses, which is convergent here at the throat at the center, and the exit radius, which is here. And then also the thrust of 4 kilonewtons, and you have a thrust coefficient here of 1.49. This also shows, so this here, the blue is your nozzle, and then you have the combustion chamber body, which is right here. This piece here is called the retaining ring, which I'm going to talk about in a second. The red here is the thermal protection system, which we've previously talked about, which protects the aluminum body from the hot combustion gases. And then these 2 holes here, these are called O-ring grooves. So they're grooves that contain O-rings, and we're going to go into that later today. But their O-rings are used to keep hot gases in certain sections of the engine so that gas doesn't like leak through the cracks between these interfaces and get into parts of the engine you don't want it to. So here's the nozzle retainer ring. So this is actually one of the pieces we need to still design. So someone, or maybe 2 people or something like that, will be working on this, making this piece, and then putting in CAD, doing the drawings, and getting it machined, and working with assembly. So this piece that we're showing is like super out of date. We've changed other things in the engine, so we need to change this. But basically, what we're using for is to fasten the nozzle into the combustion chamber and or the rocket body. That way it doesn't just fall out of the bottom. And because it's going to be exposed to really hot exhaust gases, it's not going to be using the traditional aluminum. It'll be using stainless steel, which handles the higher temperatures better. And then Raj is going to talk to us about CFD. Anybody hear Raj?
Raj? Raj, if you're talking, we can't hear you.
He's muted.
Yeah, I know. I requested Zavar's screen control and then I couldn't unmute myself, which was annoying. 1 second. So essentially, I'm going to be talking about CFD. So what Larky described there was the process of designing a nozzle. But the point is that we don't really know if this nozzle is going to work, or like we want to, okay, we have a good idea that it is going to work, but we want to confirm that it is up to scratch or it will perform as expected. So now to make sure that the nozzle is performing as expected, ideally you would want to test it in a test setup, which is experimentally tested, but usually that's really expensive. It's just kind of unfeasible to do it for every single nozzle. Let's say your nozzle doesn't work and you have to build a new one and then test it again. Just a whole ordeal, which you don't want to do. So instead, what you do is that you try and you do a simulation on it. and what you do is that you simulate how the fluid is flowing through the nozzle. So over here, if you can see, what we do is that we model the geometry of the nozzle. So here is the actual shape of the nozzle, if you can see that. So this is supposed to be the nozzle wall. And then what this is that it's a symmetrical cross section of the nozzle. So what we've done is that we've set up the nozzle such that this area, where'd the cursor go? There we go. This area is the combustion chamber. This area is atmospheric, and this is the nozzle. And then we're trying to model how the pressure changes from the combustion chamber to the exit. Essentially, could we go to the next slide, please? Essentially, what we're trying to do is that we're trying to make sure that the flow is perfectly expanded, because that's when we know that the flow is, that the nozzle is working correctly. So what I've done here is that I've zoomed into this CFD that I did of our own nozzle, and I'm showing you a cross section of essentially how the pressure gradient across the exit looks like. And as you can see that like the pressure on the right is just about equal to the pressure on the left. It looks bluer, but if you look at the scale, it's pretty close enough for us to like assume that it's nearly perfectly expanded, and gives us like a good understanding of that. Yeah, our nozzle is working correctly. Now, how do simulations actually work? Kind of complicated. I won't get into it in this one because that'll be going too deep into it. But essentially what they do is that they take physics-based equations, and then you define, on your defined geometry, they applied those physics-based equations and then essentially try and solve towards a solution. And that solution is what you're presented with. If you want to learn how to use CFD or similar softwares like FEA, you guys can message me, or a couple of other members in our team are also aware about how to use it. Could you go to the next slide? So essentially, this is what our flow will look like, and what this graph is showing us is Mach number. So blue is 0 Mach number, red is about 3 or 3.5. So right at the exit, you can see it's about 3.0, and that is the number that we get from CEA. That is what we expect. So we can figure out that, yeah, our nozzle is doing its job correctly, or at least our nozzle shape is doing its job correctly. And we can go ahead, and this design has been verified. Are there any questions about CFD? Okay, I will.
Any nozzle questions? Okay, so now, as I mentioned before, we have some O-rings in there. So for O-rings are what they're called mechanical gaskets, which basically just means that they're small like rubber loops that have circular cross sections. They're used to seal joints between different interfacing pieces of hardware and also entrap hot gases. So O-rings are actually purchased commercially, and what we do is we design the corresponding groove that they fit into. So the O-ring that we choose, we have to choose it based on several different conditions, and these include the temperature and pressure of the gas that it'll interact with, the material of that O-ring, and then how the gas and that O-ring may react when they come into contact with each other, and also the type of interfacing seal. So for example, there are many different types of interfacing seals. So what we use often, like actually what's in this picture right here, is just called a face seal, which is where you have the piece of hardware that just sits right on top, kind of sandwiches it in. And we also have another type that we commonly use called a radial seal. And they're essentially very similar, but You can use different handbooks for O-rings, such as the Parker-Hannifin O-ring handbook, which is kind of considered the most common, and it's kind of a classic, where it'll detail that for every type of O-ring seal, it'll show you like a corresponding O-ring with all of its dimensions, and also the corresponding dimensions for how to design the groove. So it's important to design your groove correctly, because as you can see in this picture, these two black, so this is a cross section, so this is one O-ring, but it's the circle coming back halfway. You can see that it's not these black things are no longer perfect circles, they're compressed. So you need to design the grooves correctly so that the O-rings are properly compressed, because when they're compressed, that is when they actually work best to seal the interface. So if they were just kind of loose in there, they wouldn't do a great job, but because they're being compressed, they can seal up the small interfaces that may exist, because the gases may easily move through them, and then if they get to places you don't want them to, that's very bad. O-rings have in the past been responsible for taking down rockets in one of the space shuttles, so it's important that you get these things right. And if you go to the next slide, I'll show you where we use all of our O-rings. So this is a diagram, a simple diagram of our engine, and also a table with the corresponding O-rings used at each of the noted locations. So you can see that, so all the O-rings are located where you have different components of mechanical hardware that are coming together. So if you look at the oxidizer tank, like if you look at O-ring 1, that's where the body of the oxidizer tank meets the end cap of the oxidizer tank. So you don't want any gas leaving the oxidizer tank, so you have an O-ring there. Same thing with number 2, it's just the other side. 3 and 4 are both for the injector, so kind of on the top and bottom of the injector, as the injector meets the combustion chamber top end cap. And then 5, again, end cap with the body. The nozzle inside of it has 2 different O-rings, one for the top and bottom, and then the retaining ring that holds it in will also have an O-ring. So many of these are actually radial seals, which means should have a picture, but they're on the side, so they so the end cap will kind of close in around it. And then it's also important to note the exposed gas. So for O-rings 1 through 4, which are the oxidizer tank and also the 2 with the injector, those both only get exposed to nitrox. So you need to take note of that, because other O-rings get exposed to both the nitrox and our paraffin fuel. So you get different combustion gases, you might get different reactivities. And then you also need to take note of like the temperatures, because it's going to be much hotter in the combustion chamber than it will be in the oxidizer tank. And then O-rings are really nice because they're controlled by kind of a governing body sort of thing, like ASME equivalent. And so each O-ring has its own cross-section area, like basically its width, and also it's the inner diameter, so you could say like, you need like a small one, like a really large one. And so they're all numbered, so it's really easy to refer to each one. So if anyone has any questions about O-rings and how we use them, feel free to yell them out, but otherwise we can move on to testing.
All right, can y'all hear me?
That's good.
All right, cool. So I'm Avi. I talked about testing a little bit back on day 1, and we've kind of heard a little bit about each of the specific tests throughout, but I'm just gonna go into a little bit more detail on each of the major tests that we're planning for this engine. So our first test, it's a pretty simple one. We're going to be doing it pretty soon. We're just kind of wrapping up the logistics of it. It's essentially just a high pressure test where we're going to push nitrogen through the feed components. And that's mainly just to calibrate our on-flight pressure sensors and to test the actuation for our main ball valve when we have back pressure on it. Like I said, this one's pretty simple. We'll be doing it pretty soon. If we can't get everyone there to kind of work on it, we'll at least have it some sort of stream so you guys can see it. And yeah, this is going to be pretty simple and it'll be fun though. Next. And a hydrostatic test. You can see the picture on the right with our boys Myron and Ashish. pictures taken moments before disaster, but it's fine. That wasn't a disaster, but I'll get on it later. It's a pretty simple test. It's essentially where we just take our pressure vessels, which would be our combustion chamber and our aux tank, and we fill them with high pressure water and gradually increase the pressure to make sure that the vessels can actually contain all of that fluid at high pressures. And last year we did one for our design of the combustion chamber at that point, and we discovered a pretty basic flaw with it, just in our sealing method. But this is the type of test that you have to do to make sure that you aren't making any sort of like elementary mistakes. And it was a very eye-opening test because it showed us this thing that like on paper works and it should work for sealing, but it's just threading and O-rings don't work. But anyway, next one. And then we'll have cold flow, and the cold flow is the first time we actually put pressurized flow through the feed system. Basically, it'll just allow us to determine our mass flow rate and the injector discharge coefficient, which is just the ratio of the actual discharge coming out of the injector to the theoretical discharge, what we'd expect to go through. And we have some losses just due to pressure and whatnot. And this will also give us a chance to make sure that our valves will be able to actuate without causing any like huge mechanical jitter that would cause any issues. And then that all the tubing can actually withstand all that high pressure without any joints having leaks or anything. Next one. Too far. And then we have, the moment we've all waited for and kind of the culmination of all other testing, which is just the hot fire, which is where we get to confirm the overall system design, that all of our systems work, that, it is a proper engine that can fire. And that's where we actually verify the burn time, so how long we'll actually be burning for and generating the thrust, and actually characterize the amount of thrust we're producing, and if there's any sort of weird thrust behavior due to any part of our construction. And this is also just going to be fun because, we get to see hot gas come out of the rocket, and it'll be kind of vindicating that we got it to work. So for all this, there's a lot of work that has to be done to write up these procedures, like, determine what our expectations and verifications are for all this. So if you want to work on, developing these procedures and that sort of thing, let me know. I'm looking to give a lot of people some work.
Yeah, so we are done with all our content. If anybody has any questions over anything we went over today, anything we went over in the past few days, anything about this whole program in general, now is a good time to ask. Yes. Or if anybody has questions about the Chinese Communist Party, none of us are specialists, but Wikipedia and Google can help us discuss.
Okay. Yeah, so again, if anyone hasn't filled out the one to meet, do that like immediately. I think most people have, at least like 13 people have, which is pretty good. As soon, pretty much by the end of today, we're going to pick out 2 meeting times, and then we're going to start having our meetings. So the first meeting that we have, just be our very next meeting, is when we're going to be talking about the tasks that we have left, which will include all of the parts and hardware that we've talked about in this whole program. And we're hoping to have like a returning member and a new member kind of work together on almost every different project. So next meeting, which we'll announce the time of sometime tonight, will be when we kind of introduce the new projects, and we'll let people pick what they want to work on, and then they'll start working. And then we'll start having 2 regular meetings a week, where the first few minutes we'll all meet up and talk about the progress we've made over the week. And then we'll probably spend the second half discussing like any issues. So if someone is saying like, oh, I worked on this kind of stuff in this, we'll kind of break it down and see like where we can go next, like what the next steps would be. Yeah, I mean, it'll just be just regular meetings, trying to get as much work done as possible, trying to stay on track and get ready to do test after tests over the course of the year. So
yeah, after this point, there's no, like I've been saying at returning members, come to this, do this, and this. Like there's none of that at this point. Like anybody who wants to help out is welcome to come to any of our meetings. we actually really would prefer you come to all of our meetings from this point on, just so that you're informed about everything that's going on. Andrew, might be wrong about this, but are we thinking of having, at least for now, meeting with IREC general meeting, at least for this week?
Yeah, so at least for this week, we'll probably have everyone come. So IREC has their kind of general meeting every Wednesday at 7. We'll send a reminder out for this. But it's we'll probably go to that meeting every now and then just because it's really cool to have all the sub-teams together. We might end up doing it more often. We might not. I know a lot of you guys are on other sub-teams with other IREC sub-teams, so we don't want to have our meetings overlap with them too often, but we do really want to have all of IREC together at some points. But it's really cool to see what all the other sub-teams like structures and payload and avionics are working on, because they're all doing cool stuff. I know a lot of you guys are working with them. But yeah, so if you're actually working on another IREC sub-team, drop that in the chat because that's really cool. We're also trying to figure that out so that we don't overlap meetings and stuff like that. Yeah.
So I was just going to say, at our next meeting, we drafted up a whole list of everything that we have left to do on the engine, all of like the parts and procedures I need to have. And we kind of assigned some of our returning members who are more experienced to be on some of them, and listed off if we want how many new members that we wanted to put on each section. So our plan is to sort of divvy up everyone into smaller groups. So there's always a new member or a new member with a returning member to help guide them and teach them, make sure everything's going all right on every single component of what we're working on. And the plan is to have everyone work in small 2 to 3 groups together and then meet together and discuss everything. And if they finish whatever they're planning on working on for the time, they'll find something else to work on. We have like a lot to do. So there's always to do. That's quite different than how other teams are doing it. We're not doing sub-teams or like any sub-team leads. It's mostly just like one task has like 2 or 3 people working on it. So if that's confusing or concerning, like please message us and ask us and give us your thoughts on it. Yeah.
But yeah, the best way is just to keep coming to our meetings and ask as many questions and try to be as involved as possible. Yeah, if there are any issues, let us know, because we won't know if there are any issues unless you let us know. So
yeah.
Yeah.
So does anybody have anything in particular they find interesting and would like to work on of all the stuff that we've gone over so far? Anything somewhere that shit's cool, I want to do that. Yes, good answer, Justin. Justin, I actually haven't asked you. I mean, you've come to all of the CCPs. I'm guessing you plan on helping out with hybrid this year, or?
Yeah, so like I'll be doing most of my work with MicroG for ISS, but I do want to work with hybrid, and then I'm not going to try to join any other IREC teams just because that would be hectic.
Yeah. Well, do you have anything you want to work on? Because I know that like you actually have a lot of past technical experience. So I'm curious to see what you'd be interested in doing.
Yeah, so over the summer I worked with Nozzles at Northrop Grumman. So I mean, you've already fleshed out the materials for the nozzle, and it's similar materials to what they use, which is a fun fact for any new members.
Really?
Yeah, graphite is a very common material in carbon-based things, as well as phenolics. I won't go into too many details because I'm not going to ruin their secrets, but yeah, some fairly similar things. And I'd be fine working on the nozzle if you needed anything additional there, but I'm content with anything.
Yeah, we actually need to do some thermal analysis stuff of the nozzle, which is that's one of the one of the new tasks that we need to do that none of us really have experience with thermal analysis. So that might be pretty fun because we definitely need help with that. George wants to do that. Okay, we'll like fully discuss this in our next meeting, but there's lots of cool stuff for one to do. George called dibs.
Is there anything we should like start learning or start doing before the next meeting, whenever that is?
Nothing crazy. I mean, if you've missed any of these, like they're all in a folder that we've shared before. And I'll share it again tonight once we post the recording of this video. We're also going to send out the slides now that they're like done. So I guess you can review them if you have any questions, but otherwise, like, we also have shared like links to our wiki. We can do that again, and yeah, that should put you in like more than good enough shape.
Yeah, I mean, the reason we did all of the crash course is just to give you like the base knowledge of like what's going on.
Right.
Like, this is like all you really need to know before you can start doing things and get like the more technical experience out of it. But wiki, great resource to find out for more information. If you want more technical information, we have a paper that like goes pretty far into the nitty gritty on a lot of things. So,
where can I find the wiki? I don't actually know if I have access to that.
oh, let me grab you the link for it right now. Hybrid. Andrew beat me. Damn it. It was a race, I knew it.
Avi beat you.
But yeah, that link that Andrew just posted is the wiki. And you can peruse around there. There's a lot of interesting things on there.
Very cool. All right, I will definitely do that then. Thank you.
Yeah, I mean, just to clarify about the wiki,
Yeah.
we've been, in the past, it's pretty common for a lot of technical teams to like have a bunch of smart people and have them graduate and not write anything down so that people can't learn from them.
Yeah.
It's strange that we've tried to write down as much useful information as we could. And so the wiki is like our way of doing that in like a pretty fast, repetitive way.
Great.
I also like to keep meeting notes of all the meetings, which I've posted up here. If someone missed a meeting, there's like text notes written out for things. Yeah, and these slides will also probably be posted here.
Cool. Thank you.
Andrew, do you want to bless us with more harmonica tonight?
All day.
Oh, I forgot we're on this tonight, actually. What am I talking about?
I should probably stop recording this, actually.
Yeah.
Okay, George, you asked about like the year outlook and kind of our schedule for the testing. We don't have a firm thing for that. We want to do our first hot fire by like early January or February, I think. And then we're just going to do the main kind of setback is just machining things right now because, you know, I'm not sure what the case is at the machine shops, but we just have to machine a couple of the last parts and then we can start cold flowing. And once we're done with that, we just need to assemble and get the fuel grains made for hot fires. That's probably our only hard date is that, like February, January next year for hot fires.
Yeah, and another uncertainty about testing is because we don't know yet what Purdue's COVID policies are going to be for Sucro. So it's like, yeah.
Things are very wishy-washy just because we don't know what we can do here at Willard. We don't know what Purdue is doing. So I don't want to set any firm dates this semester. I think maybe next semester there will be a little bit more kind of clarity with things. That's, yeah. I don't want to give any firm dates at this point just because things are too up in the air.
Our goal is to get a cold flow in this semester, which would give us a lot of data about the feed system and the injector. Also, it would verify that it works. And then there's some components that, like Avi mentioned, that we need to have machined and sent to the machine shop. So we're hoping to do that this semester, and hopefully that all that will be set and by the beginning of the second semester. So we can do a hot fire early on, and then hopefully that works.
Yeah, I feel pretty confident that we could do a cold flow in this semester.
Yeah.
And I think once we get a cold flow out of the way,
It's kind of a big jump.
Yeah. Hopefully we've been like also getting the hot fire prepped up while we're working on the cold flow too. But
And
yeah,
then for hydrostatics, we're just going to do those once we have everything machined, basically, because that's really our only firm requirement for that. I realize I hadn't asked about that.
So a lot of this stuff, like a hot fire, is something that we have never done set up prior, or at least IS hasn't done it for a while. So when we say that we have a lot to do, it's not just an actual like engineering technical stuff. It's also just like planning events, organizing people, like getting the supplies that we need, talking to people about locations, making sure everyone is safe. That's like a big part about attempting to fire a rocket engine, is that you want to make sure everyone is safe and far away. So I think a lot what everyone's going to be doing is engineering, but also just kind of like safety management as well.
Safety is a big part of engineering.
Yeah.
Yeah. I'm not trying to contradict you, so I'm just adding on to that.
No, I said it, and I was
always be thinking safe.
I said it, and I was like, that's not how I wanted to phrase that. They're very much similar. Yeah. Do you have anything else, Andrew?
No, I think it might be Among Us time.
Yeah.
It's time for me to stop this recording.
might be time.
Goodbye, CCP.
Bye.